Let's continue with chapter 11, electric current and circuits. Last lecture we defined current as delta Q over delta T, or change in charge over change in time. The units to measure current is 1 amp, 1 ampere. Relationship between current and voltage is called Ohm's law. It's is written in a form where current proportional to voltage and over proportional to resistance, or I personally like this form: voltage is equal current times resistance. We also defined resistivity, rho, that depends only on the material used to make the wire. This is the property of material, and different materials can be made in the different resistors. So if we have a longer piece of copper, it's going to have a larger resistance. If we have a thicker piece of copper, it will have less resistance. And so this is the formula to calculate resistance, knowing resistivity, rho, length of the wire, and cross-sectional area, A. Another important part here to remember that unit of resistance is ohm. And in the books, well, if you want, you can write ohm, like 5 ohms, or you can write shorter, 5, Greek letter omega. DC circuits. DC stands for direct current, as opposite to alternated current circuits where current is changing. In direct current circuits, obviously, current is not changing. That's why it's called direct current circuits. An electric circuit is a combination of connected elements forming a complete path through which charge is able to move. So what it is a path, like a wire, and there is stuff connected to in the wire, like resistances, bulbs, diodes, whatever, batteries, capacitors. So this is an electric circuit. Calculating the current in the circuit is called circuit analysis. Okay, so we're going to do circuit analysis. DC stands for direct current. The current is constant. I already said that. The current can be viewed as the motion of positive charges traveling through the circuit. This is pretty much just definition of current, that the current is equal delta Q over delta T, where delta Q is positive charges moving along the circuit. And the current is the same at all points in the circuit. This is very important thing to remember and to understand. I'm going to underline it right now. The current is the same at all points in the circuit. So if we have a path, complete path, like a circle path, like that, the current is going to be the same. You have resistor here, capacitor here, bulb here, but the current going through this loop is going to stay the same. So this is the same current going around this loop. Circuits, let's continue. There's this pretty diagram for circuit. There's the circuit number 1, or C, has a battery. This is a battery, and resistance, and the charge is moving from a positive to the negative. So this is how current is moving. And when the circuit is closed, battery is in the circuit, we have a current flowing. However, here in the picture B, we open the circuit. That means current is not flowing, current is 0, because there is no closed path. So let's read the slide. There must be a complete circuit for charge to flow. So if there is an opening in the circuit, charge doesn't flow, no current. There must be a return path from a resistor for the current to return to the voltage source. Okay, if the circuit is open, there is no current flow anywhere in the circuit. Now to solve the circuit, we're going to use 2 Kirchhoff rules. The first one we're going to talk in this part of the lecture is Kirchhoff's loop rule. That means loop. What's loop? This is loop, right? This is loop. Something goes in circle. And what's important in this law, The first, we assume the wires have no resistance, so that's written over here. And if we going around the circuit, the current stays constant. However, what is changing? Voltage is changing. It's like if the river going down the hill, its potential energy is changing. However, flow of the water stays the same. So once we going around the circuit, its voltage is changing. And for this simple circuit, we have change in potential, electric potential is equal EMF, this is voltage of a battery, and minus voltage drop through resistors, that is according to Ohm's law is I over R. So change in voltage, if we start over here, reference potential 0, electrical ground, we would go over here, we'll see battery, so it's plus EMF, and then we see resistors, so now we're losing, it's I over R, and we coming back here. Okay. Kirchhoff loop rule continue. Conservation of energy is the heart of the circuit analysis. And Kirchhoff loop rule states the change in potential energy of a charge as it travels around complete circuit loop must be 0. So if we start at the same at one point and we end up at the same point, that the delta V should be 0, change in electric potential energy 0 or change in electric potential 0. And so this explains why this, since potential energy electric is equal charge multiplied by potential voltage, the loop rule also means that the change in electric potential around the closed circuit path is 0. Let's think about what's happening to the test charge that's going through the circuit, like little positive charge, assume it's positive charge. So when it goes through the battery, it's gain energy because battery is such a powerful thing, so it gives energy to this test charge. However, when it's passing through resistance, right? When you have resistance, you're losing speed, you're losing energy. So the charge losing energy as it passes through the resistor. The energy is hence converted into heat energy inside resistor. You all know that electrical, like your phone can get warm, right? And this is why, because there's energy loss through resistors. And this energy dissipated as the heat, it shows up as a temperature increase of the resistor and its surrounding. In the resistor, the energy decreases by Q times V. Obviously, this is electric potential energy, and we can write using that the current is equal delta Q over delta T, and this means delta Q is equal current times delta T, so we plug it in over here instead of Q. And we can define power now as energy divided by delta T, so we would plug it in this expression, I delta T voltage divided by delta T is equal current times voltage. Very simple expression. So power in electrical circuits is proportional to the current and proportional to voltage. Very nice, easy formula to remember. What other formulas we had? We had the voltage is equal current times resistance. So if we would plug in voltage into equation for power, we would get the power is equal current squared multiplied by resistance. If we would plug in an equation power is equal IV, expression for current is equal voltage over resistance, then we would get that the power is equal voltage squared over R. That's part of the power. So power in electrical circuit can be calculated as current times voltage, current squared times resistance, or voltage squared divided by resistance.